All right, so a couple of updates from AICHE right there. So now they are also on the recording, so you can go see that. I looked at our schedule on the syllabus. Keep in mind a couple of things about homework 5. It's due on the same date that's noted in the syllabus, which is not the Monday coming up in like 2 days. It's also not the Wednesday where most homeworks would normally be due. It's due the Monday after that. So there was a 2-week period for homework 5. So don't kill yourself trying to do homework 5 by Wednesday, because it's not due until the following Monday. Yeah. Sorry, guys, I can't hear the question. The reason you have more time to do homework 5 is because we cover everything, all of the stuff that took us 4 weeks to do in batch reactors, we do in 1 week for flow reactors, because a lot of it hasn't changed in terms of the content. However, that doesn't mean that the problems are necessarily solved any faster, so I gave you more time to solve those problems. So the content comes a lot faster, but I know the solving doesn't necessarily follow, so there's a little extra in there. Yeah?
So have we done all knowledge for next homework?
Not yet. So we need the thermal equations, we need the energy balance, which is, we're going to start that today and finish it up Monday and do examples on Wednesday. And then your homework's not due until the following Monday afterwards. Any other questions on homework? Nada? Okay, so like I said, we're going to come back to this example a couple of times. We'll add some energy balance terms to it after we introduce the energy balance. But I had also noticed on the schedule that I thought we only had today and Wednesday or Monday to do the energy balance, or sorry, today and Monday. We actually also have Wednesday, so my original plan at the end of Thursday's lecture yesterday was to just post the solutions for this. We have enough time to actually go over them, and I think that could be helpful. This type of problem is what the first 3 look like on homework 5. So the ones that are the California PE exam problems, they're more doing stuff like this that you can actually solve it by hand. That's why the little by hand symbol is on all of those. So I thought it worthwhile that we actually work one of these out in more detail, which we had gotten close to on Thursday, but I just want to finish it up for about the first 20-25 minutes. And then also show how this translates over into MATLAB. So we'll actually, I won't type code, we'll write code up here. Much the same way that you would be expected to write code on either exam 2 or the final exam. We'll leave a couple of steps out just for time. But this will be a good example to come back to. And then at the very, maybe last 15 minutes or so of the class, we'll try to get to the energy balance so that we can use that again on Monday and Wednesday. So where we had left off, I'm going to have to make a couple of sketches. Sorry, AICHE, it's nothing personal, but we need a little more space here. Where we had left off was a plug flow reactor, or sorry, packed bed reactor. How do we know it's a packed bed reactor? The biggest giveaway for a packed bed reactor is that we were told the weight of the catalyst that's inside there. So initially, if you just look at something like the rate constant K, that doesn't really tell you by itself whether or not this is a packed bed or a plug flow reactor, especially when it's only got a unit of time. However, here, when you have W is 100 kilograms, that's telling you how much catalyst is inside your reactor. So if you're trying to keep a mental picture of what this looks like inside the reactor, this thing is packed full of catalyst, and by the time you get all the way over to this side of the catalyst here, if you are a little gas molecule that has flown through this particular reactor, by the time you hit over here, you have been exposed to 100 kilograms of catalyst. So at the inlet over here, you've been exposed to no catalyst, so 0 kilograms. And by the time you make it to the other side of the reactor, you've been exposed to 100 kilograms of catalyst. So that's what we mean with these differentials when we're talking about something in terms of catalyst mass or, for that matter, volume. With the bed density here, yes, bed density here, you could equally say that you have been exposed to a certain volume, and those mean exactly the same thing. So let me see if I can move this down a little bit without, yeah, of course you would do that, wouldn't you? For some reason, copy pasting also brings back anything that you erased, which I'm going to call a bug and not a feature, because we didn't want that. So instead of, like I said a couple of times, we can move back and forth between these equations. We can either talk about something per weight of catalyst or something per volume of reactor. So if we wanted to deal with this system in terms of volume, we could also say that at this point, if you're a little molecule of gas, you've been exposed to 0 liters worth of reactor. By the time you make it all the way over to the other side of the reactor, the volume that you've been exposed to would be equal to the weight of the catalyst divided by the bed density. And so that would be 100 kilograms divided by 2 kilograms per liter. And so by the time you get over here, you've taken up 50 liters. And so those could become the bounds on your integral. For example, if you had to do this within MATLAB and you wanted to solve it over a particular span, you could either go from 0 to 100 kilograms, or you could go from 0 to 50 liters. It just depends on which way is most appealing to you when you're setting the problem up. Typically, if you are doing a packed bed reactor, most of them will be in terms of mass. So you'll typically go as a W span instead of like a V span. But if you do know the bed density, you can switch back and forth between these at any step of the problem solution and always solve it in terms of the other one. I think the way that we had solved this yesterday, I don't have to think, I can look. We solved it in terms of catalyst weight, so I'm going to stick with that particular solution. The solution that we had come up with, we were asking for the variation in conversion as a function of catalyst weight. And we had said that that is equal to minus RA prime over FA0. So the part that I didn't get to do last time was to actually write where each of these came from, which is what I would like to take a couple of minutes to do now, since we have this available. This part came from saying that XA is equal to 1 minus FA divided by FA0. And that part hadn't changed. That looks very, very similar to what we would have seen for a batch reactor. So for the batch reactor, it was XA is 1 minus NA over NA naught. So I'll put batch stuff over here. So that was, we went from our original material balance, which was dF dW is equal to RA prime, to this by using the definition of conversion. If you have a multi-reaction system, like multiple well, not multiple species, yeah, more than one reaction, generally you don't write this differential equation. You use the full differential equation in terms of molar flow rate, so you would have left it like this. If you had multiple reactions, where now your RA is your net rate. That element hasn't really changed at all from batch reactors, but we didn't do that because we only have a single reaction. So we skipped right to the dXA. And then the next part that we did was we worked on the RA prime. So we had dx dw was minus K. Actually, let's step back one before we do that. The RA prime was equal to minus RA divided by rho bed. So all of that over FA naught. The reason that we can get away with this, and this is unique to packed bed reactors, we haven't seen anything like this prior. The rate of a RA prime, remember, has units of something like amount, so something like a mole or a kilomole or something like that, per mass of catalyst, so kg dot second. And so the conversion factor that we saw between the two of those was that this is equal to the same old RA that we have seen before, divided by rho bed. So that was a new relationship that we had seen before. That's another relationship you need if you ever want to move in terms of your differentials from with respect to W, so like a dW, over to something like dV. You also need that particular relationship as well, if for no other reason than just to make the units work out. The next step we had taken was to work on the RA, which for an elementary rate law, because our reaction was just A goes to B, that just looks like RA is minus KCA. And that part hasn't, again, changed at all from a packed bed reactor. So we had rho bed down here and FA naught. So this one was RA is KCA. Again, if you have more reactions, then this rate law looks like a net rate instead of an individual rate. If they're reversible, then some of those rates will have equilibrium coefficients in them, or sorry, equilibrium constants. That particular element, again, hasn't changed at all from the batch reactor, nor has our definition of, at least not our effective definition of CA when you're talking about which CA shows up over here. The next step is the part that has subtly changed from a batch reactor, but not enough that it makes a terrible difference in the way the equations look. Was there a question over here? Thought I saw a hand up. Pavlovian response. So if we want to work on that CA, the CA that we need here follows a similar definition as what we had seen in the batch reactors, except it's FA over V. So that V, I'm not putting the caps on there. That V is the volumetric flow rate, V. And if you compare that to the way that we had done this for a batch reactor, we had said that was NA over volume with a capital V. So that's a subtle difference. The reason that that's a subtle difference is because if we're dealing with a gas, it's never the case where we can't, or it's never the case where we don't have to use that giant expression for CA0. We always have to use that expression for a gas in a plug flow reactor because it can move back and forth along the axis of the reactor. The volume is never considered constant in that particular sense. So this part is one that I think we had skipped over a little bit in the last lecture. So I'm just going to write that out in a slightly expanded form here so you see where everything is coming from. So the CA that we have to deal with here is always going to be FA over little v. FA we can attack in the same way that we had for something like a batch reactor. So this would look like theta A minus the stoichiometric coefficient of I over the stoichiometric coefficient of A times XA. So that numerator in there will end up looking like 1 minus XA. I just wanted to remind you of where that is coming from. The bottom portion of this is the part that takes up a lot of space. So this was V0 times, I always forget which pattern these go, T over T0, P over P0, and FT over FT0. So this denominator term here came from the ideal gas law. So we had actually derived that. I think earlier on when we first introduced batch reactors, we had derived that particular expression. This is the form that you should use if you have multiple reactions. Yeah. Oops, yes, you're right. It should be one on, the T and the P never have the same pattern. So this is P0. Thank you. So that's the general form that you use when you have multiple reactions. The reason that you use it when you have multiple reactions is because of this term. And actually it should, the top part is not used for something like that. It's just the bottom part that's used for something like that. I'm going to define that right now. So this is the part that's for multiple reactions, the reason being because of how FT and FT0 are defined. So FT looks similar to the total moles that we would have had for a batch reactor. It's the sum of all of the molar flow rates of I. Similarly, FT0 is the sum of all of the inlet molar flow rates. And generally, when you have a multi-reaction system, these are the parameters that you sort of have access to inside of like a MATLAB script. And so this particular form is much easier for that V term on the bottom. The form on the top, you don't really have an option for that. It has to stay in a fairly complicated form, but that's okay. If you have a single reaction, then this term goes back to what we had seen for the batch reactor. That term, after you simplify everything, goes back to 1 plus YA naught times delta times XA. So that there's a subtle difference there between what happened with the batch reactor and what happened with the flow reactor, mostly because in the denominator now we have this ratio of the sum of the flows instead of the ratio of the sum of the moles. That's the bigger difference. The numerator up here for a multi-reaction system basically just stays as FA. And that's why we typically set up, as we'll do in a couple of minutes, we set up our differentials in terms of FA so that we don't have to worry about what comes after the right of that. For example, we don't have to use an extent of reaction afterwards because our differential is set up in terms of FA originally. So we just access FA instead. We'll see an example of that in a moment in the code, and I'll point it out. So we have two different versions here. The way that we had ended up writing ours for this specific example was that CA would be equal to, actually we can just leave it as that, FA0 times 1 minus XA. The delta for our expression was 0 because we had the same number of moles being formed as the number of moles that were being consumed. And also the temperature was constant, so we didn't have to worry about constant temperature. And then we just had a question of whether or not the pressure was constant or not. For the first part of the problem, it was. For the second problem, part of the problem, it was not. So that pressure term shows up in the denominator. And then there's what's the one other term that's in the denominator there? The V0. So that's, remember, the lowercase V0. So this V0 is the inlet volumetric flow rate. So that was kind of the one step that I had skipped over pretty quickly in the previous lecture. So it's described in slightly more detail here. What we had ended up with was a differential that we would then have to integrate for x. So if you were to substitute what we just found into the differential, it ends up looking like dxa dw was equal to k. Our inlet volumetric flow rates canceled, so we have the rate constant k times rho bed, and then times 1 minus xa. And then we kind of had a question as to whether or not the pressure stuck around or did not stick around. If you just assume that it does, and you bring it up into the numerator, then you have something that looks like P over P0. So that got flipped because in the previous expression, P0 over P here was in the denominator, and then I flipped it the other way around so that it's in the numerator here. That flipping back and forth can be an annoying algebra process. And then our initial condition for something like this is almost always that XA is equal to 0 at W is equal to 0. Typically, we have no conversion entering a reactor. When we get to more of the design elements later in the course, after we do CSTRs, the other type of reactor, sometimes that will not be the case. If you have one reactor here and then it goes through a heat exchanger and enters another reactor, you may have to solve that system initially for the first reactor with no conversion, but the second reactor does have conversion. And sometimes your inlet condition will change there. If we go ahead and solve this for part 1, you would end up with something like XA is equal to 1 minus the exponential of rate constant K divided by inlet volumetric flow rate, density of bed, times W. Ooh, there's a negative sign up top too. Don't forget that. So you should at least take a moment whenever you get an expression like this, if you just want to check your math, figure out what happens in the extremes. So in the extremes, I know when W is 0, I had better get my initial condition back. So if W is 0, I had better recover this. And so if I put W is equal to 0 right here, I will get the exponential of 0, which is 1. And so 1 minus 1 is 0. Thankfully, we have started where we need to. And if I want to understand at least a little bit about where we're headed, I could set W is equal to infinity in this particular case, because if we could theoretically have a bed as large as we want, we could set W is equal to infinity, and we would end up getting the limit of something like this would be 1, which is 100% conversion. We can assume from the shape of this, it's an exponential, that it'll probably curve up and asymptotically approach it like this. If we wanted the actual plot, of course, we'd have to stick it in something like a calculator or a computer to plot it, but that's roughly what would happen for something like this. The key feature for this, though, was that it was for problem 1, which had no pressure drop. Yes?
Did it reach 1?
Yes. No, actually, it strictly does not reach 1 for any finite value of W. If you put W is equal to infinity, yes, you will get to 1, but we can't actually design a reactor that has an infinite amount of catalyst in it. So you can get as close to 1 as you want, but you can't get right at 1. So this was the case for no pressure drop. For a case where we had pressure drop, then our change was that instead of this being 1, we had this term as, where did I write it? The quantity of 1 minus 0.003 times W to the 1/2. Where does that come from? Either you're given that form, if we're making things simple, or on the project, you have to use either the Bernoulli equation or the Ergun equation to get a differential form of something like that, and then you just have to solve it. Typically in MATLAB, if you get lucky and you just have the Bernoulli equation, you can sometimes get closed forms that you can actually solve by hand. It only happens if the system is pretty simple. It's not necessarily an assumption, it's just the units of your, or the way the problem was defined works out in such a way that that actually simplifies. Sometimes it can be more complex than that. So if we wanted to solve something like that, our differential then looks something like this. So we have dxa over 1 minus xa will be equal to k over V0 rho bed times 1 minus 0.003 W to the 1/2 times dW. Don't forget that because the pressure drop is a function of how much catalyst has been exposed, it needs to be on the right-hand side of your integral, because that's, or the right-hand side of your equation, because that's the integral we're going to take with respect to W. So anything that's got a W term has to go over on the right. Anything that's got an X has to go over on the left. If you forget and move W over to the left, you won't get the right answer, because that essentially assumes that W inside your pressure drop is constant, which it's not. So these integrals then look like 0 to W and 0 to X. Or sorry, XA. So this is for the part 2 of this problem where pressure wasn't constant. If you solve something like this, you get a similar looking expression. I'm not going to write it in quite the same closed form. You can practice all of your algebra and your calculus on this. V naught rho bed times a slightly uglier expression here, 2/3 times 0.003. It's not going to fit. That's an X as in times, because there's another part that comes in down here. 1 minus 1 minus 0.003. Fun, right? 3/2. Like that. So doable by hand, not the world's greatest integral to try to do by hand. But this one has a slight change from what you might expect in the other problem. The reason being, if you were to plot P as a function of W, That's going to keep going down and down and down and down until it eventually reaches 0. After you have exposed the system to a certain amount of catalyst, eventually this will go all the way down to 0. That represents the maximum amount of catalyst that you can have in that particular reactor before you run out of pressure to actually drive stuff through. What this is describing is that if you were to try to turn that reactor on, the flow would initially come in at some velocity, and then it would start slowing down. So these arrows would get smaller and smaller and smaller and smaller, until eventually you hit some point here where you don't have enough pressure to drive anything anymore. So this would look like W max. And so you've got a slightly different higher limit for the amount of catalyst you can have in this problem because it has pressure drop. We can't flow things through to the point where P is equal to 0. If P hits 0, you stop flowing things through. You really don't. If you get to that particular point, all of this math doesn't really matter anymore because we had assumed it was steady state to begin with, and you're accumulating stuff inside your reactor now. But it does set that upper limit. If you're just slightly below W max, you'll get stuff to go through your reactor, which is fine. So there is an upper limit for conversion on this because there is an upper limit for pressure. That's an upper limit you'll want to keep an eye on for your project, because some of the way that your project has been worded for some of those problems is run the simulation until a number of different events occur. One of the events that can occur is that the pressure drops below some minimum pressure. Usually that minimum, if you're dealing with absolute pressure, it's 0. If you're dealing with, if you're dealing with gauge pressure, it's 0. If you're dealing with absolutes, it's usually 1. Because at that point your pump isn't doing anything anymore, it's just atmospheric pressure. So that's one difference for pressure. Hold on to that, try to code it in MATLAB as we're about to do, because that'll look very much like your project. So we've still got about 10 minutes for code, and then we'll have enough time to get over to the energy balance. What if we wanted to solve this in MATLAB? Again, I said that a lot of times in MATLAB we end up writing these things in terms of the FA parameter here. So our differentials are originally written in terms of FA, so the differentials that we're solving, where did I put the differential? I guess here would be fine. Instead of solving this differential, we would end up solving a differential that looks like dFA dW is equal to RA prime. The reason being, if we're dealing with something that has to be solved in MATLAB, it's probably helpful to have access to those molar flow rates. Not always possible, but often helpful. And so that's what we're going to solve here. The answers that you should get for this would be the same as the other one. Within reason, we have to make one assumption. Yes?
To go back to the previous stage, I think your integration on the left is wrong. It should be negative natural within 1 minus x.
There's a negative over here.
Yeah, but the other side should also have a negative, so there should be 2 negative and the entire thing should be positive.
Could be. I'll have to check it after class. That's the one that I had checked before class, so I'll double check it again. So if we wanted to do this in MATLAB, what would the function or the script look like? This will look somewhat similar to the kind of stuff that you might have to write on an exam. We would always start off with the same differential equation structure that we had for a batch reactor. So we start off with a W span instead of a T span, and that would run from 0 to 100. You do not have to add comments on your code when you are writing it by hand on an exam. That part hasn't changed. Similarly, your initial condition hasn't changed very much. I'm going to write this one a little bit more explicitly than we might need to. We don't really need to do anything more than FA0, but I'm going to include FB0 just so that you can see what would happen if I had, for example, a multi-reaction system. We would just tack on more flow rates. If we had a system whose pressure drop is described by a differential equation, there could be a pressure here, and a non-isothermal system would have a T as well. So those could be there. Don't change my color. And then our solution looks pretty much the same. So WSol, YSol is ODE 4.5 in pretty much the same way that we would have used it in any other case. So you can call that function whatever you want. It's a function of W and Y. And then you include your W span and Y0 in the same way that you would have for a batch reactor. So that element looks pretty much the same. The only thing we've changed is we call this thing up here W instead of T span. We're going to integrate everything in the same way. Since I'm going to set all of these differentials up in terms of flow rates, we would, after we're all done, we would also need to calculate that XA is 1 minus the flows of A, which is going to be in the first column, divided by the initial A, so Y0 of 1. So we didn't explicitly use a differential in terms of conversion, so I'm actually calculating the conversion after we solve the system here. And then if we needed to plot it, that would come afterwards as well. So this would look like plot WSol XA. And it just occurs to me that this actually needs to be YSol up there. Just do that on your paper. Won't be that bad. All right, so that looks like the general approach that we would have for any other piece of MATLAB code. The advantage of writing this thing in terms of flow is what happens next, because you have to keep track of a lot fewer equations as you go along. So the function that you would end up having doesn't look too much different on the definition line. So it's still dy dw is whatever your ODE function is. The difference is what happens next on the remaining lines. Having access to the flows means that you can, in the first few lines there, write what is the flow. So the flow of A, FA, is Y of 1. And the flow of B, if you need it, is Y of 2. And so these will immediately have the units of whatever flow you happen to have. So for example, molar flow rates are often moles per second, maybe kilomoles per hour, something like that. And now you've got those to work with directly. You've also got any of the initial conditions that you might have. Usually those come right after this particular line. So I'm just going to write all of the ones that we have. I'm not actually going to define them all the way down. So the other things that we have would be things like FA0, FB0, P0, little v0, so the volumetric flow rate. Any of the constants that we have, so things like rate constants, that sort of stuff. I think that covers pretty much anything. Anything that we haven't defined that I haven't listed there, they all go there, right? We just type them in as whatever number they happen to be when we solve them. When we move forward after that, the challenge with plug flow reactors when we have a gas phase reaction, again, was this giant mess up here on the top. That's the part that gets really easy if you choose to write this in terms of molar flow rates instead of something like concentration or conversion. The reason it gets really easy is because we only have to write this line once. Right? We have to write that once, and then we don't have to worry about it anymore. We can just use the actual volumetric flow rate for everything else. So what do I mean by write that once? I mean exactly that, write that once. Leave a little bit of space above this because we're going to need it. So we would have a line somewhere that just looks like V is equal to V naught times T over T naught, P naught over P, FT over FT naught. And so this will have units of something like cubic meters per second. Maybe it's liters per second. Actually, I think the unit we were given, wasn't that liters per second? Yeah, we might as well keep it consistent with that. This would be liters per second. So So we get to use that once. Just keep in mind that anything we need inside there has to be defined prior to that. So the T over T naught, we don't worry about that because that would have been 1 anyway. So we can actually erase that or cross that out if we want to. The P naught over P, well, we have an expression for P, so we can add that directly above that. This is equal to P0 times 1 minus 0.003 times W to the 1/2. And so this will have any of the, whatever the units of pressure happen to be. They don't always have to be bar for something like this because we're not dealing with equilibrium. Bar is not a bad one to use though, just so that you don't have to keep switching back and forth. And so now for the very first time, we have to actually use the independent variable, which in the differentials for batch reactors was always T. Here it is W, but we have access to W already because W was the input. So right here is why we have access to W. We don't have to define W anywhere. It's coming in as an input to the function. And so we can just use W as it is. For example, we don't have a line that looks something like W is equal to W of 1. You can do that if you want, but that's redundant because there's only one element to W. So we've already got W. And then the other element that we need are the two FTs that we've got. So we've got an FT0 here and an FT up here. So we would need to define both of those as well. So for example, FT would be equal to FA plus FB. But that's pretty easy to write because again, the very first two lines of this code, we have FA and we have FB. So we don't have to try to do any odd looking conversions right there. We need the other one for FT0 as well, but that would look kind of scrunched, so I'm not going to write it right here. The big advantage of this is the CAs. So you never have anything as a CA that looks any more confident or complex than FA divided by V. Right? That's the entire expression for CA, which looks a heck of a lot simpler than something like this. Right? That particular form for CA doesn't need to show up anywhere. You don't need anything more than the original definition of CA over on the left. And that's one of the big advantages of writing it in terms of molar flow rates. So much of this stuff simplifies if you actually know what the molar flow rates are. A lot of the complexity of the stuff that we have over here comes when we introduce X's and we don't want to deal with molar flow rates for some reason. That's when things get nasty like what we've got on the right. Sometimes that's required. So actually for this particular problem, there's a very good reason we can't write it in terms of molar flow rates, which is we don't know what the inlet molar flow rates were. So this particular approach would need another piece of information. So it's not always possible. That's why we have the other techniques, because sometimes we don't know enough to use this technique. But very often, and certainly on the project, you will be able to use this particular technique because you'll know the inlet molar flow rates. All of the other species, concentrations look the same. So this is FB over V. And then when you want to write the rates, those are similarly simplified as K times CA. Right, so those elements of the code afterwards become much more easy to troubleshoot and really much easier to write as you go through each one. That's why MATLAB is kind of nice. The remaining elements of that code don't change much from the differential one, from the batch one. I'm just going to draw a dotted line over here. The remaining lines that you have would look something like dFA dW would be RA divided by rho bed. And then when you're all done, you have to accumulate all of these as you would with a multi-reaction system for a batch reactor. So this would look like dFA dW, followed by whatever else you happen to have. So that's the big advantage of trying to do something in MATLAB, is especially on a liquid phase, maybe you don't see that much of a difference. It doesn't make a big difference. On a gas phase, it helps you a lot because the only time you have to deal with that nasty equation for volumetric flow rate changing as you go down the reactor is once. Everything after that gets handled automatically by the way you structured the code, which is great. Do that for your projects. You don't want to try to do it in terms of conversion. Well, you can't do it in terms of conversion because it's a multi-reaction system anyway. So what we'll do is revisit this particular problem as we develop our energy balance, and we'll add additional terms to it. We'll keep the pressure in there. By the time we're done, we'll have a single reaction with pressure drop and with thermal effects, with a jacketed reactor going either way on the jacket. And so this will look like a miniature project. The elements that we're going through here are the same elements you would need on the project. We'll also introduce later in the class, when I might have to just post a video on it, but there's a nice trick you can tell MATLAB when to stop solving a differential when one of these conditions happens inside the integration method. And we'll use that because it'll make your life easier. You won't have to try to interpret ODE solver errors, which is always fun, interpreting those errors. So our friend, the energy balance. We've already done it once in detail. We're not going to do it in detail again because so many of the steps look exactly the same. The big difference between what we did last time and what we did this time, last time the, what do you call it, control volume that we used was the full volume of the reactor. The control volume that we use for a flow reactor is a volume element. In the same way that we used a volume element for the material balance, we define a volume element for the energy balance as well. And so that volume element will just indicate like that. So if the flow is going in from left to right, as it enters, it's been exposed to some volume V. By the time it goes through our volume element, it's been exposed to V plus delta V. We're going to leave out shaft work. There's almost never any mixers inside of a plug flow or a packed bed reactor. That doesn't really work when you dump a solid catalyst in there. It's kind of hard to spin something around. So the only thing that we're worried about is Q. So we're going to assume that any amount of energy that goes into the system, so we're calling it delta Q because we're dealing with a differential amount. It's typically over the entire volume. But it'll be plus if it's considered added to the system. So if we're, for example, heating it up, it'll be plus because it's coming in. If we've jacketed the reactor and we're trying to cool it down, it would end up being negative because it's going out. So that's all the energy through the walls. All of the energy through the flows, that wasn't supposed to be so long, is the sum of all of the molar flow rates coming in times their enthalpy of each species coming in. That's a little dangerous. I don't want you to think that that zero is part of the inlet. So instead of that, it's not like inlet to the reactor, it's what is it at volume V, right? It's inlet to our differential element, not inlet to the entire reactor. So I'm not going to use the zeros because I think that could be confusing. Coming out on the other side is the same thing, molar flow rates times enthalpies, but now they're just evaluated at a different location. So here they're evaluated at V plus delta V. So as long as you know your enthalpies as something like joules per mole of whatever species you're doing, you multiply it by the molar flow rate, and that's the amount of energy that's being dumped into your system just because there's flow coming in and out. The only one that we have to fiddle with a lot is the enthalpy term. All the fiddling that we had to do with the enthalpy term for the batch reactor is the same fiddling that we have to do here. So I'll present those steps. We're just not going to go through the algebra of actually substituting them in and rearranging like we did for the batch reactor. But that way you'll be able to see what those assumptions are. The other term that is new this time, actually, sure, we can talk about that. The delta Q term that we've got is defined in a specific way. There are many different ways you could get energy to go into this system. They're almost all due to a temperature gradient, which is why we call this thing Q. Most of the time, that's because there's another fluid on the outside that's adding energy or removing energy. You could also have something like an electric heater, and then this form of Q that we're going to introduce is not accurate. You'd have to find one for an electric heater. But almost always this form of Q is because there's another fluid outside your reactor that's either adding or removing energy. The first term that's there is a U. That U is the same U that we had before, which is the overall heat transfer coefficient. I'm going to write this letter in A as A, but as a gray A, because we're going to have to work on that. Remember, we're dealing with a differential amount of space right here, so it's not really just A, it's the differential amount of area A, because we've just got a little thin slice of our reactor. And then all of that times a temperature difference, so T minus TA. Remember, TA here, that's your coolant temperature. And the other T is the actual temperature of your reactor. That differential element A is the one that we have to work on a little bit. The way that we calculate that differential element A is to use a different parameter, which is little a. We can leave that in gray. The way that we do that is little a times a delta V. And the reason we do that is because we can actually calculate this little a based on the overall geometry. So the little a is the total area of the reactor, the surface area of the reactor, divided by the total volume of the reactor. So if I'm a cylinder, what I'm going to do is calculate the total volume of that reactor, so pi r squared times L, that'll be the total volume. If I also want to calculate the surface area, that's the surface area of that particular cylinder, so that would be pi d times L. When you are all done with that, an awful lot of those terms end up canceling out, and as I recall, it's 4 divided by the diameter of the reactor. So if your reactor is a cylinder of some particular size, you can simplify that expression quite a bit. But the delta A element, or not the delta A, the little a is a feature of the geometry of your reactor. So I think all we're going to have time for is the last step, and then we'll simplify this. If you do an energy balance on this system, it's the same old accumulation as in minus out plus generation minus consumption that we had before. And so what we end up with is 0 is minus, UA times delta V times T minus TA plus the sum of Fi, Hi evaluated at V, because that one's coming in, minus the sum of Fi, Hi evaluated at V plus delta V. If you take that entire expression divided by delta V and take the limit as V goes to 0, you end up with the equation that we'll have to play around with on Monday, which is UA T minus TA minus the derivative with respect to volume of the sum of Fi, Hi. And that ought to look, if you dig back in your notes to when we did the energy balance for a batch system, we had something pretty similar to that. You should be able to compare the two. The next part that we'll have to deal with on Monday is how do we make that something a little bit more meaningful. We'll end up in roughly the same location, which is a differential of T with respect, to V or W, and then a bunch of other stuff on the other side. End up in very, very close to the same place in terms of what that equation looks like. That's all I got. Enjoy your weekend. Don't kill yourself. Remember, it's not 2 days from now that the homework is due. It's like 9 days from now that the homework is due. The following Monday. Thank you all. Have a good weekend.